Alright, so welcome to the first technical lecture for Intro to Structures. Today we'll be discussing static equilibrium and idealization. The learning objectives for today are to review the basic concepts of loads and static equilibrium. Then we'll discuss the idealization of members and connections types, which is probably something you haven't seen yet. And then we'll talk about how to create free body diagrams. And we'll put all this together to fulfill our objective of computing reactions for statically determinate structures. So when we mention loads in structural engineering, what we're really talking about are either forces or moments. Forces in 3D space are vectors, and they generally act along our coordinates of interest. So in 3D space, we have a total of 3 independent forces, x, y, and z, as you see in the left. Moments act around the axis of interest, and we also have 3 total possible independent moments in 3D space. And these are usually drawn, as you see here, where the x moment acts around the x-axis, the y moment around the y, and so forth. Now, moments and forces are vectors, and they're related by another vector, r, which we typically call the moment arm. Those 3 quantities are related by the function you see here, where the moment is the cross product of the moment arm and the force. So we can say that the force passing through point A generates a moment around point C equal to r cross F. Now if we simplify this to 2 dimensions, the cross product of r and f reduces to the product of the perpendicular distance between point C and the line of action of that force passing through point A. So we have a simplified relationship where the moment is simply the perpendicular distance times the force. Given those definitions, it's pretty simple to see that if A and C lie on the same line, the moment around C from F will be equal to 0. So in this case, the answer to this question is 0. Now, in civil engineering, structures are designed to satisfy static equilibrium, or Newton's first law. This implies that the structure is at rest, so it's not moving. The structure does not translate. That means that the sum of the forces add up to 0. And the structure is not rotating, which translates to the sum of moments is equal to 0. There are 2 ways to think about forces, as external or internal. But any way you slice it, these conditions for static equilibrium need to be met. So let's think about external forces first, then we'll move into internal forces. Let's take a free body diagram for an ideal weightless beam, AB, which is supported vertically at both ends. The supports generate what we call reaction forces. And these are very generally labeled using the variable r. We also have applied loads, which are applied directly to the beam. These can be point loads, which we usually denote with the variable p, and they can be point moments, which we denote with m. Now, the applied loads have fixed values, or assigned values, whereas the reaction forces simply change to preserve the static equilibrium condition. So they will try to cancel out the applied loads. This also works if we think about the structure internally. So let's take that very same structure with reactions and applied loads, and let's make a cut, AA. Note the way that we denote the cut with the dashed line and the 2 letters. When we slice it, everything that was on the left goes to a left-hand free body diagram, including the loads. Everything that was on the right goes to a right free body diagram. And now, in order to preserve static equilibrium, we need to take into account the internal loads within the beam. So these would include an axial or normal force, which we denote with N. It would include a shear force or vertical force, which we denote with V. And it would include a moment, which we denote with M. Notice that the direction of the arrow indicates the positive convention that we use in structural engineering. And note that the convention flips depending on whether you're looking at the left cut or the right cut. But we'll talk about this more in later lectures. So in almost all cases, the applied loads are known and the reaction forces or reaction moments are unknown, so we need to solve for them. We can do that following these steps. So the first thing is to identify the object of interest. This can be an entire structure or it can be a piece of the structure which we've cut using the method I just showed. Then we draw a free body diagram showing all external forces if there are no cuts. If there are cuts, we need to show the internal forces as well. So I should update this. Then we resolve forces into the X, Y, and Z axes, and we set the sums to 0. We also pick an appropriate point, any point in the structure, and we set the moments around that point to be 0. And finally, we solve all these equations, potentially 6 equations. And if, for example, we still don't have enough equations, we can go back to step 1 and repeat the process with a different slice of the structure until we do. All right, so let's put that in the back pocket for a moment, because in order to do this, we need to know what reactions we're solving for. And in real structures, that's not so easy to determine, because the connections and supports can be a little bit tricky. So we need a way of idealizing structures into a framework that we can analyze. And so let's take, for example, this horizontal beam on this building, which is attached at its ends to some of the supporting girders. We want a way to idealize these connections into a set of reaction forces. So what this would look like is, first, we may idealize the connections as, or we may idealize the beam as a straight line, and then idealize each connection as, for example, a hinge or a pin and a roller. Okay? And we'll talk about exactly how to do that. And then finally, we can model this beam as a vertical reaction and horizontal reaction, R1 and R2 on the right side, and a vertical reaction, R3, on the right side. So let's see how to do that by looking at the different types of ideal connections. We'll start with supports, and we'll start with the pin support. So in steel structures, the pin support looks like what you see on the left, right? Literally a pin. And the pin keeps the structure, or keeps that member fixed in both the X direction and the Y direction. So it's only able to rotate around that point. In the concrete structure case, it's not necessarily a pin. It just depends on the amount of rebar that's used. So in this case, we have one line of rebar, not too much. And so essentially that rebar will keep the whatever is attached there to move laterally and vertically, but it won't provide much moment restraint. So the concrete that is cast in that location will pretty freely be able to rotate. So we think about a pin, or we draw a pin as a triangle on a grounded base, as you see there. And we model it as a support reaction in the vertical direction, which we usually call Ry, and a support in the x direction. The next type of ideal support would be the roller. And in steel structures, the roller can be either a rocking mechanism or a rolling mechanism. Both of these mechanisms provide support only in the vertical direction, but they allow lateral movement and they allow rotation. In concrete structures, you will also see roller types of supports, which allow, again, movement laterally, and they allow rotation of that joint. So in this case, the forces used to model the roller are just vertical forces. Keep in mind that the roller, the ideal roller, can also support in the opposite direction. So it is also possible to have to apply a downward force, even though technically these mechanisms would not do that. The last type of idealized support is the fixed support. In steel structures, a fixed support would be something like a fully bolted base. So you can, if it's hard to see, but you can see how this beam goes onto a base plate here, and then that gets bolted down all around. So that provides quite a bit of rigidity and resists movement in both lateral directions as well as vertical, as well as rotation. In terms of concrete, again, we go back to, we need to look at the rebar layout. So in this case, you can see partially exposing these columns, you see a rebar cage, which is now rectangular. That provides a lot more rotational stiffness, and so we can consider that a fixed support. Okay, so a fixed support supports both X, Y forces as well as moments, and we model that as literally just a beam going into a grounded base, as you see here. And in this case, the reactions will be 3, Ry, Rx, and a moment. So now we move into member-to-member connections. These are different in the sense that they now model internal forces, whereas supports model external forces and moments. So the pin connection for steel structures looks like what you see here, where the beam is connected generally at the web. And if you don't know what the web is, it is this vertical part of the beam. In contrast, the horizontal portions are what we refer to as flanges. All right, so by connecting only at the web, you do allow some degree of rotation at this connection. And so generally we assume that these types of connections don't have any sort of moment restraint. In practice, they look very similar. You can see in this case that there is a clear gap here and here, and so the only support is really coming from this connection here, which is at the web. So there is some degree of rotation allowed. Okay. In concrete structures, again, it comes down to rebar. Very hard to tell from the outside, but in this case, this is a fairly sparse mesh of rebar, so you would expect it to be able to rotate somewhat around that particular point. And when I say rotate, I'm really talking about relative rotation of the beam versus the column, right? So I would expect some sort of angle to develop there in this configuration. Again, we're talking about very large forces, right? The way we model a pin, the way we draw it, is essentially as a circle with the corresponding connections or the corresponding members coming into that circle. And it is modeled the same as a pin support with both horizontal and vertical reactions, but no moment. Okay, so the pin cannot resist any moment. There's also the fixed connection. Okay, in the case of steel structures, this is evident when you see a lot of support being added to the flanges in this case, right? So we see, for example, welds at the flanges. We see connections at the flanges. We even see stiffeners in the supporting column to add a little extra stiffness so that the supporting column doesn't move. So in this case, this creates a very rigid system, which essentially will rotate together, and that's really what we mean by fixed connection, is that that whole corner basically stays at a right angle the whole time. And again, if we look at real structures, we see things like welds at the flanges. We could also see bolted end plates like you see here. Okay, so that again is providing very rigid type of connection. In concrete structures, you guessed it, comes down to the rebar layout. Here's an example of a very dense mesh, and this is definitely going to cause that connection to be very stiff. Okay. We draw fixed connections simply as two connecting beams with nothing. Sometimes we may draw them with a little triangle there, but that's not necessary. Okay. And in this case, the fixed connection is going to provide all three types of support, moment, and the two forces. So in summary, here you have a list of ideal supports. Notice that, for example, the roller will change the direction of support, whether it's horizontal, as in this case, here versus here. We also did not cover the horizontal slider or the vertical slider. These are sort of like rollers, except they also provide moment support. Okay. And then we have two basic types of connections, the fixed and the hinge or the pin, which you also have here for your reference. So let's actually work a few examples, and I would like you guys to pause this and see if you can get it on your own before continuing. But we have our actual beam here, and the idea is to turn this into a beam line model with supports at both ends corresponding to this real case. So let's go ahead and do that. I will draw the beam, and I have on the A side what is a connection purely at the web So I'm going to say that is a pinned connection, but because I want it to be essentially a support, I'm going to draw it as a pin support instead. So, and on the other side in B, this is essentially lying flat on a support member. Okay, so that basically does not limit anything other than vertical motion, right? So I assume that the beam is free to rotate around that point, kind of like a rocker. So that's going to be, for me, a clear sign that that is a roller, right? And I put the load in the same place. And so my reactions will be AY, AX, and BY. Let's go to the second example. We have an actual beam here. In fact, we have two beams. And so your job is to come up with two idealized beams and make sure you note the internal forces as well. So let's go ahead and split that into two beams. Okay, we'll start with beam AB. If I look at the connection down here, I notice that there's a lot of support happening at the flanges now, so that is very clearly a fixed support. If I look up here at the top, again, I see that there's a connection here connecting the flanges. Those are the stiffest parts of the beam. And so I'm going to, again, assume that's a fixed connection. So that is going to have internal forces and internal moments. Okay, and those are going to be reflected over here. Okay, make myself some room. Okay, and then I finally have my applied external force here. So these would be my two free body diagrams. An alternative, if you didn't want to worry about the internal forces, would be simply to draw it like so. Right? So this again denotes a fixed connection because I didn't draw a pin there. And the only thing that's left are the reaction forces, which would be AY, AX, and a moment around A. And those would be the same for this free body diagram as well. Okay, so that deals with how to get from a real structure to a free body diagram. All right, so let's talk a little bit more about that particular case. Now, I'm assuming you guys are familiar with this already, but if we have inclined forces, then we simply need to resolve that using the angle. Okay, so when we have a force that looks like this at an angle phi, the adjacent component is going to be equal to F times cosine of phi, and the opposite component is going to be equal to F times sine of phi. If we have distributed loads instead of point loads, we can usually simplify those to a point load for statics purposes. And that simplification is done using the following formulas, where the equivalent point load is equal to the area under the distributed load curve. Keep in mind that distributed loads are expressed in terms of force over distance, all right? And the The point of application for that load is obtained using the centroid, by finding the centroid of the distributed load, which is the integral equation that you see here. Most of the time we'll be dealing with special cases of distributed loads, which are usually uniform loads or linear loads. In these cases, you should know already the solution to those integrals. For the uniform loading case, the force will simply be applied at the halfway mark, and the force will be equal to the distributed load times the length. In the case of a linear load, the centroid of a triangle is actually at 2/3 its length, and the total area is 1/2 of the distributed load times the length. Okay, so these are formulas that you should already have, or that you should have memorized, so you don't have to solve those integrals every time. Now here's a very simple example for a free-to-buy diagram. So if we have a structural system that is pinned and roller supported with a force applied at an angle of 10 kips, we will note that we can resolve that force into its proper components by doing the cosine and sines operations like I showed. And then we turned it into a free body diagram by drawing the corresponding forces. Okay, so again, the pin at A has vertical and horizontal supports, so we can draw those. And then the roller support has only a vertical support, so that's our VB. And then finally, we can invoke the equilibrium equations, right? Putting together everything we've learned so far. So sum of the forces in the x direction, right here, that is balancing the horizontal reaction with the horizontal component of the force. That should be equal to 0. The sum of the forces in the y must take into account both reactions as well as the vertical component. Okay, and then the sum of the moments must take the moment around any point. We just need to pick one, and it is beneficial to pick point A just because there are two forces going through that point, and so that means that those forces apply 0 moment and we can remove them. And so that leaves us with the applied force, the vertical component, and the vertical component of VB. And so we multiply those by their moment arms and we have our final equation. Okay, so this is my moment from VB, and this is my moment from PY, we'll call it the Y component of P. Should have included the 5 feet in there. All right, so that's how you would do it, and then you simply solve this set of 3 equations for the 3 unknowns, HA, BA, and VB, and you have your full definition of your system in static equilibrium. So that was a simple example. Now here is a more complicated example which I will leave for you guys to solve, and I will publish the solution handwritten so you guys can check your work. It is a hinged arch, okay? So just to give you a little bit of forewarning, if we look at the supports for this particular structure, we will see that there are actually 4 supports. And doing a global static solution like we did before will only give you 3 equations. So you won't be able to solve for all 4. So you will need to do an additional step where you slice this somewhere and calculate internal forces in order to fully solve it. So I'll leave that up to you guys to figure out, and I will publish the solution so you guys can check your work. So in summary, we learned that in order to perform structural analysis, we must idealize real structures into ideal supports and connections that we can analyze. But it's important to understand that these are simply approximations of real behavior. They don't fully describe it. And a lot of times, the biggest errors that we make in structural analysis actually come from these idealizations, right? Not accounting for the full range of behavior. No connection is fully pinned or fully fixed. They're always somewhere in between, right? And so we need to be conscious of that. But in order to carry out an analysis, we need to be able to talk in these terms. And secondly, we showed how reactions can be solved using free body diagrams and equilibrium equations. And this process can be repeated until we get enough equations to solve for all of our unknowns. Now, I will make a special caveat here as well, that this is only applicable for determinate structures. And we will find out what that means later on in the class.